Hi, my name is Tommaso Lenzi, and I'd like to tell you a little bit about the research I've been doing with my students at the Bionic Engineering Lab. As you may know, lower limb amputation severely affects the quality of life and mobility of millions of individuals. Our goal is to develop better technologies that can address the unmet needs of this population. When we look at the prosthesis technologies, devices have evolved from fully passive systems to variable impedance systems that can change the damping of the joints as you walk, to hybrid and semi-active systems that can strategically inject energy for some portions of the gait cycle or only for some activities. And finally, to fully power prosthesis that can replicate the full spectrum of torque and power generation ability of the biological leg. Unfortunately, though, the ability to imitate the biomechanics of the biological leg comes at the cost of increased weight. And weight has some negative effects on the users. For example, it increases the metabolic energy consumption, the temporal asymmetries, and the residual hip effort. And this is true, of course, not just for walking, but also for other activities like climbing stairs. Even more importantly, increasing prosthesis weight has a negative effect on the socket stability, which is already a really critical component of the prosthetic system. So the goal of my research in the last 5 to 6 years has been to develop a prosthesis that is both lightweight and power. So one thing that I've learned is that there isn't really a single magic component that is going to address this problem. You can't reduce the weight of a power prosthesis just by changing the motors, by changing the battery. It is about the harmonization of all the passive and active components that go into the prosthesis. And in order to achieve this harmonization, what we do is we rely really heavily on brute force optimizations, where every single component is simulated from the required joint torque and speed to the thermal system, voltage and current, strength of different parts. And although that may take sometimes weeks to have full solution of this optimization, then we can use the simulations in order to understand how design choices that we make affect the overall performance of the device. So one critical issue that you have in power prosthetics is that biological joints and the knee especially really require you to provide a very high range of speed and torque. And unfortunately, when you look at DC motors, they really only work well for a very narrow range of torque and speed. And outside of these narrow range, the performance in terms of efficiency and power output decreases dramatically. But what's interesting about the knee is that if you divide torque and speed requirements for different activities, you see that there are some activities that require high torque and low speed, such as ascending stairs or descending stairs. And then other activities like walking require high speed, but not so much torque. And so in theory, if you had a gearbox that can switch gears between activities, then you could use your DC motor in a way that is way more efficient, leading to a smaller battery and lightweight battery, and also to a smaller motor. So now the problem with gearbox, of course, is that in the attempt of increasing efficiency, you may add some weight in terms of mechanisms. And so what we did is we have to invent a new variable transmission system, which we call actively variable transmission, or AVT. And what this is pretty much an option slider crank mechanism with a varying crank angle. So pretty much we have a 4-bar mechanism, 5-bar mechanism with 2 degrees of freedom. And what we can do with the additional degrees of freedom, the one that changes the length of the crank, is that we can regulate the transmission ratio. So as you can see in this slide, the transmission ratio not only changes the function, the position of the knee joint, which is common in any 4-bar mechanism, but it also changes the function of the length of the crank, which we can regulate actively through a miniature application. So you can see these that, for example, for girls king as and not the ratio for ascending stairs for higher torque. And then also we have used high ratio stairs actually torque over the lowest gain. Here, both now we go back to a low transmission ratio. And so, of course, there are some limitations in this. We require about 200 to 250 milliseconds to make the switch, depending on what activities. And also, we can only switch gears when the knee is not moving. And the reason why we decided to do it this way is so that we can make an active variable transmission that is very lightweight. And just to give you an idea, this system that you see here on the left cat model is only about 60 grams. So something that is very important for a power prosthesis is to have a very low joint impedance. And this is important because through a low joint impedance, you can swing your leg freely, and also you can regenerate significant amount of energy during walking. And so, as you can see in this table, which I have adapted from a paper that was recently published by Bobby Gregg's group at the University of Michigan, we actually were able to achieve the lowest joint impedance in the field. And we were able to do that by coupling a very small motor with a very low inertia to a relatively low transmission ratio, which we can achieve thanks to the actively variable transmission only for walking. And in fact, with experiments with amputee individuals, we observed that we can actually regenerate about 3.3 joule of electrical energy during walking, which helps making the recharge of the batteries as you walk, and therefore minimize the weight of the battery for your system. And so, how can we achieve this without sacrificing torque or speed? Well, certainly the ABT helps, right? Because we can get more torque for stairs when we don't need as much speed. But there's another thing that we did, which is very important. With an offset slider crank, like the one that we're using in the knee, the position of the motor is fixed with respect to the frame. And so what we did is we designed the frame to wrap around the motor and work as a heat sink to enhance the thermal design of our device. The reason why we do this is that the amount of continuous current and therefore continuous torque that the motor can provide is a function of the heat that the motor can dissipate. And so same things for the powers. The amount of power that the motor can produce is proportional to the capability of dissipating heat. And so what we saw with simulations and through experiment is that by using the frame, designing the frame to be heat sink, we could double the continuous current of the motor, which means we can use that small motor, 150 gram motor, instead of 120 watts nominal to 240 watts continuously, indefinitely. What's even more exciting is that thanks to the enhanced thermal design, the frame working as heat sink, what we can do is that for 10 minutes, we can operate that motor at 440 watts. And this is extremely critical. This means that, for example, when you are climbing stairs, you can go up to 150 Newton meters of torque for pretty much 40 flights of stairs, which is really, really high number. So that's great, but what about the ankle? Can we do the same thing with the ankle? Can we use a gearbox in the ankle? Well, unfortunately, when we look at the biomechanics of the ankle, and specifically you can see here the torque and speed during walking, stairs climbing, and stair descent, the answer is kind of no, you can't. And that's the reason why you cannot use a gearbox. It's not useful to have a gearbox is that the reason really is separation between high torque task and low torque task. And so we resorted to something completely different. We resorted to a polycentric design. Now, polycentric systems have been used in prosthetics since the 1950s. That's not novelty there. What we did that is quite innovative is to optimize the polycentric mechanism to work with the active motor and transmission system. In other terms, we've used the polycentric mechanism to reduce the amount of torque that needs to be produced by the motor during walking, and also to reduce the load on the actuation and several components of the device. And the reason why we can do this is that with the polycentric mechanism, the instantaneous center rotation is not fixed, but is moving. It changes with the position of the joint. And also, it is outside of the physical location of the device, as you can see in this slide. And so, long story short, we can achieve a much smaller ground reaction force arm and at the same time a larger actuator moment arm. And so here you see the device, and you can find the details of this the polycentric ankle, power polycentric ankle device on a paper recently published on Robotics and Automation magazine. And as you can see, it's very small and lightweight. It's actually only 1 kilogram without the electronics and including the foot kilo. And despite being so lightweight, we were able to achieve torque in excess of 140 Newton meters during walking with transtibial amputees testing. So one component you probably have seen and read in this device, and we spent a lot of energy and effort on, is an instrumented pyramid adapter. So ground reaction force sensing is extremely important for good control of prosthesis. And unfortunately, what you see is that load cells that satisfy the range of forces and torque required for ambulation and prosthesis especially are actually very heavy. They could be 300-400 grams. And then on top of that, you have to add a lot of electronics for the conditioning of them, and of course some interfacing components. And so what we did is to resort to completely different transduction principle using magnets and Hall sensors, and we have integrated these into a pyramid adapter, which is only 150 grams. So you can see here the knee and ankle module combined with the section view of the leg, and also a polished up picture of our device. As you can see, all the control electronics and the batteries are contained in the knee module, and then they connect to the ankle. So now what we've achieved is a device that is the first time both powered and lightweight. The Utoh Lightweight leg closely matches the weight of hybrid and semi-active devices, and also variable impedance devices, which is pretty exciting. But of course, the question is, does it work? So we've been testing at this point for about 3 years with individuals with above knee amputation, and we've first been able to approximate the biological leg behavior for common activities like walking, as you can see here, and stairs climbing. And more recently, we started kind of pushing the boundaries and trying to understand what a lightweight and high power, high torque leg can do. We have developed a controller that gives users the ability to change foot clearance voluntarily as needed to cross over obstacles of different sizes and walk without having to recognize that the obstacle even exists. We've also been developing sharing your controller that gives users the ability to change online, voluntarily change the assistance provided by the knee as necessary to walk, squat, and lunge. And also, we have developed adaptive stairs controller that can synchronize with the movement of the user as necessary to climb steps of different height at the desired cadence, and not only 1 step at a time, but even 2 steps at a time, as you can see in this video demonstration here. So while we push the boundaries of mobility for individuals with above knee amputation, we're also looking at other subjects, and specifically, we're trying to shift the focus on elderly and DYSVASCULAR users. Those users that, with available devices, are considered limited community ambulators. And thanks to the lightness of our device, we think that we can address the needs of this population. So this is just started, but we're having really exciting results. For example, one study saw that the subselective walking speed power is compared to micro, exceeding the threshold in this case for community ambulation, which is 0.8 meters per second. We also can improve on cytosens transitions, and what's interesting about this is not just about the energy injection part that seems to be very helpful for these users, but also the removal of energy, so the negative power phase seems to be better compared to microprocessor control needs. And finally, as expected, of course, the highest gain in ambulation is from the stairs, where we can climb step over step. And what's exciting that you can see here in these slides that when we use the power prosthesis or this DYSVASCULAR, the user can pretty much match the timing in stair ascent of a young, strong G3. So what's next for us? This is all very good and exciting, but we think there's still something missing. We think that being constrained to lab testing really prevents us to understand how people can benefit from a powered prosthesis. And so what we can do, what we want to do, is to actually test at home. And unfortunately, our device, the one I just saw before, is not really able to achieve this goal. And so what we did is that we have developed a new device, which we call Utoh Bionic leg. And this device is specifically meant for home testing. As you can see in this slide, it is very small, even smaller than the previous device, the Utoh Lightweight leg. And despite that, it has been designed to satisfy ISO standards. There are no exposed mechanical electrical components, and also there is a completely custom embedded electronics for maximum efficiency. What's interesting about the device also is that we now have 3 power joints: the knee, the ankle, and the toe. And as you can see in this section view here, it's a very compact device. And one thing that we have to change conceptually is that we have to move away from the actively variable transmission. And we actually came out with a novel solution, which is a torque-sensitive compliant transmission, which we think is going to combine the benefits that you typically see from series and parallel elastic actuators with variable transmission systems. And so what we have now is something that continuously adapts the transmission ratio based on the torque and speed demand. And that's how the leg looks like when we put it together, which was just a few weeks ago. So actually, we were able to test it with Alec, one of our research participants, just 2 days ago, and I'm really excited for you to see the demonstration, which is available on the workshop website. So thanks so much for your attention. I really want to acknowledge the contribution of all my graduate students you see here, but also my collaborators, both at the main hospital here at the University of Utah and our local VA in Salt Lake City, which is right outside campus here, and also collaborations, the physical therapy department. And finally, I acknowledge also the support of National Institute of Health, National Science Foundation, and Department of Defense, which are supporting our research. Thank you, and I'm looking forward to your comments and your questions. Thank you.